documentary filmmaker. He has worked with PBS, Discovery, and has produced and written 24 programs for the National Geographic channel, ranging from renewable energy to the X Prize. Sam studied creative writing at San Francisco State University, is a longtime member of AAAS. He has spent 3 summers on Devon Island near the magnetic North Pole and was a member of the founding crew of the Mars Society F-Mars station in 2001. In 2002, he joined a crew at the MDRS station for the one-of-a-kind ICO-MP experiment. Sam loves snowboarding, journal writing, dancing a fast 1930s swing step. I have met my match. Awesome. And in 1995, he and his wife, Linda, spent their honeymoon riding a motorcycle to the Arctic Circle. Some notable quotes about Mr. Burbank include the following. Sam Burbank is elevating the video journal to an art genre. Kim Stanley Robinson, author of Antarctica, Red Mars. Sam is a true artist who makes visible to the eye what before could only be seen by the mind. And Robert Zubrin, author of The Case for Mars, says he is magnificent. Please make welcome Sam Burbank and his fantastic panel this afternoon.
Check the mic. There we go. Okay, welcome panel. Welcome. Thank you, Janet. Great. Wasn't sure where I was going to make my opening remarks, but it's going to be next to Seamus. Great. Thanks for coming out to our panel today. So I was so glad when Chris asked me to chair this panel. If any of you ever desire to chair a panel like this, the key is to get with Chris over drinks and just talk about stuff. And then he'll know what you like and what you really are interested in. For me, engineering off Earth is the stuff of dreams. It's literally the stuff we think about when we're kids and we think about space. You start to imagine. I grew up in the rich 70s when so much great space art was being produced. Very fanciful, delightful, impossible, but maybe not impossible stuff. And so here we are. My background, Janet, those were mostly lies. I'm teasing. So I was lucky. I had 3 summers on Devon Island with Pascal Lee and his merry band of early Mars astronauts. And in 2001, I was lucky enough to be a part of the first F-Mars crew, the inaugural crew in this Mars spaceship-looking contraption that Frank had erected the year before without the tools expected to erect the thing, as they had crashed out of a C-130 with the parachute that didn't open. So here we are in this thing, and they had big plans for how the first spacewalk should look. So they chose a couple of heavy hitters, Pascal Lee and Charles Coquelle, a great astrobiologist, and a couple of my heroes, these guys. I was just very excited for what was going to happen. They closed the door. They had a Discovery Channel camera in there with us. And immediately, our plumbing system broke. Immediately. And so the first spacewalk, we were in a sim. We were supposed to do this properly in sim and not cheat. So immediately the first spacewalk became the engineers, me and Frank, out to fix the plumbing problem. It was a good story, and it actually really showed, I think, more clearly that the kind of exploration on Mars will not necessarily look as heroic as we want it to look. It might be a bit messier, and our system was particularly messy because it was the toilet system we were working on. So you may hear me ask some skeptical questions tonight about some of the fanciful and delightful stuff we'll talk about, because the way I look at things is they're just always going to break. But with that in mind, I will switch this over to the panel. And I think I'll go ahead and introduce people as we go here instead of introducing the full panel at once. And we'll turn this thing right away over to Seamus Tuohy. Seamus works with a company called MDA. They're a Canadian company, and he is their right-hand man here in Huntsville, Alabama. And from there, Seamus, tell us what brings you here.
Sure. So like I said, I work at MDA Space, which is primarily known as the Space Robotics Company. We did the shuttle arm. We do operating the station arm right now, and the Canadian government's committed to building Canadarm3, which will go on the Gateway. All this stuff is in space. So that's been our history. We've probably done more space robotics operations than anybody else. Long duration exposure, you talk about things break. Our stuff hopefully hasn't, I know it hasn't yet, hopefully never will. It'll go through its design life. But as we're thinking about Moon to Mars right now, we're talking about getting down on the surface. Yes, with robotic arms, but also with mobility systems. So like a lot of people, we're looking at what a rover system would look like that would help the astronaut. Ours has an arm. If it's an MDA system, it's almost required to have a robotic arm. And we look at these as being astronaut assistants, that they not only do mobility, which means doing work while you're transiting, but also relocatability, which is a tough word. I'm getting used to saying it, which means you pick up at one location, move to another, and place it in another location where it does its business, whether that is a hab module or a sensor station or what have you. And so we're looking at being the tool company, and which is fine. Develop rovers, develop autonomy systems, develop arms, develop payload management systems, and with an eye towards how you go from a number of tools that you put on the surface of the Moon to how those would translate to Mars. And I've said tools a bunch of times because to me to us that's the big challenge is how you go from tools to infrastructure. And it may be a distinction without a difference to a lot of people, but the way I think of it is that tools are things that help you build, and so you're constantly bringing new things. You're constantly bringing like I don't have the correct Allen wrench. I need to get a new tool. Infrastructure is stuff that's always there that you're going to use, that's available to you, and it's for you to use for planned things, but it's also for you to do unexpected things like fixing toilets or what have you. And as we go from operating the way we do now on station to operating on the Gateway, Moon, and then to Mars, things like at first, we may have an astronaut present, so it's really in situ control. There's somebody there who is real-time looking at what the robot's doing, hopefully staying out of the way. And if they're not controlling it directly, they're supervisory control, but they're present to something which is near real-time, which the delay to the Moon is very short, but they're a tiny one, and there are communication dropouts, and there are links you have to go through. But then to Mars, where it's really remote, the time delay there really precludes you, if you're not there, or you're not in orbit, or not close, that operation really is a remote operation. And in that way, we're going from a human in the loop, where the system is dependent upon the human being present and making all the decisions, and doesn't do anything without the human saying, yes, go forward, to being a human on the loop, which the Department of Defense kind of defines as you're there kind of monitoring what's going on, but if it's doing fine, it's going to go do its stuff. But you're just sitting there on the loop monitoring what's going on. You're there for contingency operations. To fully autonomous. And when we get to an infrastructure element, that's probably where we need to get to, is something that's autonomous. Maybe no humans are even watching it. Maybe it's out of communication, or if something has to operate so quickly you can't get the humans there, or whatever situation is, they have to be able to operate autonomous. And as we talk about building up an infrastructure, initially everything's going to be brought from Earth. And I look at this as being mission-oriented. And that's kind of the way NASA does a lot of things right now, which is I have a mission that has a particular goal, and I build a spacecraft to do that mission, and I launch it on a launcher for that spacecraft. And so it's a vertically integrated, single-use system to where if we have presence on the Moon and on Mars, it's sustainable. You have to do stuff in situ. You have to live off the land as much as you can. And it's not mission-oriented. It's almost enterprise-oriented. It's like going from doing what NASA would do for a science mission to what maybe the military does for doing its missions, where it knows what assets it has, it knows where they're located, and how do you put them all together to accomplish something that maybe weren't even planned for at the beginning. And to me, that's the key of how we go from using these tools to become infrastructure so that we can go from missions to a sustainable presence. And those are things that MDA we're going to be worried about, supporting the U.S. space program and the Canadian space program.
Great, thank you, Seamus. Next up, we have Mark Hilburger.
Right, thank you.
Mark is a senior researcher of structural mechanics at NASA Langley. Is that fair?
Yeah.
And away we go with Mark.
Yes. So my background is structural mechanics. Recently, I joined NASA's Space Technology Mission Directorate as one of their principal technologists. I cover the area of materials, structures, and now construction. And when we talk about construction, we're talking about construction of infrastructure on the moon and onto Mars. And so while it's not an area that I was too familiar with when I was first asked to take on that job, it's been a tremendous pleasure to start learning about all this fantastic stuff. It really is an exciting time. I can't express that enough. So my role as a principal technologist is to identify technology needs and then develop and advocate for investments and try and put forth sensible investment plans to meet NASA's goals, as well as accommodate industry's goals as well, as we start working more with industry and trying to foster an economy, cislunar economy, and hopefully beyond that even. So that's really my role. And so what I'm going to try and do here very briefly is go through a few slides to give you just a taste of the types of things that my group at NASA is working on. And so I like to start with what we call the Envision Future slide, and us PTs and other system capability leads that work at NASA have drawn up these Envision Futures to sort of take a look at what could be possible, right? And what our vision is, in my case, for infrastructure and how we would build it. And so here we have autonomous lunar excavation, construction, outfitting. That's my area. There's probably a dozen plus other capability areas, and if you want more information, I have to put the plug in for NASA's techport.nasa.gov/framework website, and you can get just a tremendous amount of additional information that I'm not going to be able to go through. And there's other capabilities in there, including ISRU and power and autonomy and robotics and all that stuff. So my area is autonomous lunar excavation, construction, outfitting, looking at the technologies that are going to be required to build sustainable infrastructure. And so it covers quite a broad set of capabilities, and we start with the upper left there, excavation for ISRU-based resource production. So that's mining ice and regolith so that we can extract hundreds to thousands of metric tons of commodities per year, as well as gathering regolith for the production of construction materials such as aluminum or silicon and iron and that sort of thing, at least on the moon. Then on the lower left, we have regolith manipulation and site preparation. So that's pretty much what you think it is. It's moving regolith so you can prepare sites for construction, but also manipulating regolith to use it in the form of, say, berms or overburden to provide radiation protection to habitats and that sort of thing. The middle section here is highlighting construction and outfitting. The previous set of speakers started talking about outfitting, and this is going to be a tremendous challenge, right? As soon as we start wanting to construct in situ, especially, whether it's assembly of truss structures or it's 3D printing of habitats and that sort of thing, how do we outfit these things with plumbing and electrical and data and all that stuff? And ideally, we would do that autonomously with robots. Types of construction considering like tall towers for solar power, communications. We're looking at the construction of landing pads and roads, unpressurized shelters, and then pressurized habitats. And then the final circle there really is just to highlight the fact that we're trying to do this together with industry. We can't do it by ourselves. And so partnerships with industry and all the expertise that we have in industry is really an important part of our strategy, but it also paves the way for commercial capabilities in the future so that NASA can go on and do the important things on Mars and leave the cislunar environment to a commercial entity or entities. So I'll just spend a couple minutes on some of these specific areas just so you get an idea of the type of things that we're either considering or currently working on. And so I'll start with excavation for ISRU. We're looking at developing capabilities to autonomously, essentially year-round, extracting and delivering materials to ISRU processing plants. So we're talking thousands of tons of material a year. We're traveling many kilometers from, say, the extraction site to the processing facility. And so these really are blue-collar robots. These aren't our scientific white-collar robots. These I wanted to call them gals and guys, but I mean, they're really working hard, and they're coming in contact with some really hazardous environments. So when we talk about some of the real challenges, it's not only making these things lightweight, but it's making them robust, but it's also understanding that you're going to have to repair them. So we're talking about modularity to affect repairs and maintenance over time. The types of configurations that we're looking at are excavators. You see on the lower left the ISRU pilot excavator being developed at NASA Kennedy Space Center. And then one of our successful public-private partnerships. This one in the middle here is a Redwire. They won the Phase 1 Break the Ice Lunar Challenge, where they designed an excavator and hauler system for ISRU delivery. And then also we're looking at even developing just the implements. So for example, ultrasonic blade bucket. And the reason why ultrasonics or advanced types of implements are important, and this goes into, say, one of the main challenges, is when we're operating on the moon and we're trying to excavate, not only are we doing it with a lightweight system, but we're at reduced G. So you think about terrestrial excavators, they're really massive, right? And so they produce all their traction and pushing force based on their mass. Well, we have lightweight and we have reduced G. And so one of the real challenges is, how do you excavate and overcome or provide force, or maybe you don't provide force? And so that's where this ISRU pilot excavator is really unique, in that it has this dual counter-rotating bucket drum design, which theoretically counteracts all those horizontal forces out. And so now it's able to dig successfully, and they've done a great job of doing that. The ultrasonic blade bucket attacks that problem by reducing the blade force that's required to cut through material. So I wanted to highlight the ISRU pilot excavator real quick, just to show you that we really are developing some really unique capabilities here. So in the upper left, this is the excavator operating in a regolith bin at Kennedy Space Center. They call it the Swamp Works. And so you can see it's very carefully going through and just skimming the top of the regolith off the surface. And they don't want to dig too deep in it because this regolith can clog really easily. So they're very careful about how much regolith is going into each of those scoops. It has an automated regolith excavation mode where it's constantly monitoring torques in the motors and that sort of thing, so it can adjust the height of the buckets and the rotation speed and that sort of thing. It can also identify some, a hard obstacle in the ground maybe that you didn't anticipate, and so you have to get away from, for example. So it's constantly monitoring its situation and adjusting. The bottom images are just to show some contingencies. We're not going to purposely drive over a set of rocks, but they wanted to show that, if it did find itself in a precarious situation, that it would have the ability to, adjust its center of gravity, like it's shown in the lower right, or, just the ability to use all the buckets and wheels to traverse over something complicated. So, not shown in this video, but they do have the ability to do what we call gravity offloading, which is to, hold it up by a hoist and simulate the type of traction you would have in a 1/6 G environment. And they've been able to demonstrate that this operates in those conditions as well. So really cool stuff. And it's on track, funding, hopeful. that we can do some sort of lunar demonstration in the 27, 28 timeframe. But that's my hope. We're not officially manifested on anything. But
I know that these are just the introductory statements here, but what is the scale of the thing we just saw, and the weight of the thing we just saw?
That's probably about, maybe 90 kilograms, but it's a pretty good size. It's about this big.
It's bigger than it looks.
Yeah, I've operated it, actually. So it's a pretty good size.
Very good. We'll talk more about that thing
Yeah,
later,
sorry.
that concept
I'll
later.
keep rolling it around. But yeah, I just thought that was really unique. And it really pinpoints one of the points I want to make is that terrestrial concepts aren't necessarily going to translate directly to off-Earth concepts when it comes to, say, excavation and construction. In this case, it's lightweighting and low G, and completely changes maybe your thoughts on how you design something. The next area is regolith manipulation, site preparation. Has many of the same challenges as excavation. You want lightweight, durable systems. They obviously have different missions, where they're trying to grade, level, compact, and prepare sites for construction. NASA has in the past done work. You can see in the upper right the NASA chariot with a dozer blade. Then we fell off for a little bit, but we're starting to rekindle our work in the area of site preparation. We have some great public-private partnerships going on in SBIR and STTR activities. This, the one in the lower middle there, Astroport did a design study for a modular system that can be reconfigured into like a hauler and all sorts of different infrastructure elements. And then to the lower right, a lot of university involvement. This one is a Luster grant given to the Colorado School of Mines to develop a grader compactor system. So hopefully this time next year, we'll have videos of some of these systems as well. But obviously something very important as we talk about construction. So moving to construction, and I promise I only have one more thing after this, when we talk about construction, there's really different flavors of construction, and we break them up into classes. Class 1 would be your standard prefabricated, pre-outfitted can that you have in ISS, and that's served us well. Obviously, ISS has been a very successful project, but it's not a sustainable sort of approach to extended habitation on the moon and onto Mars. And so we're looking to sort of change the paradigm and move towards Class 2 and Class 3, Class 2 being assembled structures or deployable structures, and Class 3 being ISRU-based additive construction. And obviously the reason why we're excited about those types of technologies is assembly, for example. You could imagine erecting, like on the lower left, a tall power and comm tower. That's a 50-meter tall tower with a 200-kilowatt electric array and a 5G communications antenna on it. But you can see yourselves wanting to cast all those truss members out of regolith material, right? And then have a robot there that can assemble them, and that sort of maybe laser weld or something like that with aluminum. Or panel and truss type construction. You see a blast containment shield concept that we came up with, where you're assembling very easily some truss and panels into the blast containment shield, and then you're backfilling with regolith to provide energy absorption, that sort of thing. And then moving on to Class 3, again, another nearly 100% ISRU-based solution. So all looking towards sustainability and long-term construction of expansive infrastructure. And so I wanted to finish with one final video. So a lot of emphasis has been put on additive construction, rightfully so, because I think it's a very versatile technology. But some of the earliest infrastructure, and I mean like within the next decade, I think can be accomplished, this is Mark's opinion, can be accomplished through assembly. It's the type of technology that we already know how to do. It just comes down to space rating a lot of these components and that sort of thing. So what you see here is a concept of maybe a first functional communications and solar power tower that you land on a lander. It has a specialized jigging assembly frame, but it has COTS, off-the-shelf robots with specialized tools that grab the truss members. Also have the attachment end effectors that in this case you'll see rivets. That's for a ground demo for later this year, but ideally we'd have something like laser welding or something like that. So you're not messing with all rivets and that sort of thing. But this is the type of thing that I think is something that can be done near term, and really start to jumpstart our understanding of how to operate and build in space. Here we're showing the rivets, but you could very easily see yourself doing spot welds or something like that in place of that. A lot of vision system, a lot of autonomy being developed here at NASA to help with precision assembly and that sort of thing. Obviously extensible to other structures such as blast shields and shelters and possibly pressurized habitats and that sort of thing. And so, yeah, I love talking about this stuff because it's so cool. It just reminds me of my Erector set when I was a kid, building up stuff.
Yeah, one of the things I think that you shock yourself sometimes when you see a video like this is my first thought is, where are the guy lines, right? There's no wind on the moon.
Yeah.
Right. Every environment has its own.
That's one of the benefits of
pluses and
6G.
minuses, but there's a plus.
Yeah. The design loads are a lot lower when you don't have to consider wind or ice. We do have to worry about thermal, and thermally induced deflections and that sort of thing. There's the seismic activity on the moon and those sorts of things. But yeah. So,
great. Okay, Mark. Thank you very much. Okay, next we're on to Melodie Yashar. And Melodie is with a group called Icon. She is they do 3D printing. I saw a wonderful example of their Mars Dune Alpha structure today on the web, and among many, many others. So with that, take it away, Melodie.
Thank you, Sam. Hi, everybody. I'm Melodie, as Sam mentioned. I'm the Vice President of Building Design and Construction at Icon. At Icon, we develop large-scale additive manufacturing technologies for both Earth and space. Today, I'll tell you a little bit about the work that we're doing for our space applications purposes, much of which has emerged of late as a result of a Phase 3 SBIR award that we've been awarded to develop additive manufacturing technologies for the lunar surface. Myself and Jason Ballard, the co-founder of Icon, were both repeat contestants. In my case, I was a repeat winner within the 3D Printed Habitat Centennial Challenge, which took place between 2015 and 2019. Several industry companies and partners were identified as a result of that challenge, and Icon began an extended collaboration with NASA Marshall, particularly the Moon to Mars Planetary Autonomous Construction Technologies project, thinking about how we can use and leverage additive manufacturing technologies to create surface infrastructure on the Moon and eventually Mars. So in the last several years, my team and I, architecture and building performance at Icon, in addition to several other architectural and civil engineering partners, have put together our idea of what schematics for an initial lunar base might be. And we've used that and leveraged that design exercise as a means of generating and deriving hardware requirements for a construction system on the Moon that would enable the creation of various types of horizontal and eventually vertical infrastructure. So this is our vision for a sustained lunar presence. As Mark alluded to, additive manufacturing, and in particular, in our case, 100% ISRU regolith-based construction will enable the sustainable creation of various types of surface elements without having to think about how you custom design these individual elements. Instead, you can send up one robotic system, one construction system that can create a wide variety and great versatility in structural types and uses. So as I mentioned, we're looking into how to create first horizontal construction elements such as landing pads, roadways, and then eventually thinking about how we can develop vertical construction elements. So basically berms, unpressurized structures, and eventually habitats that are pressurized and certified for human occupancy. Of course, this can't happen all at once. So in our opinion, this needs to be part of a phased development plan, as well as an overall kind of scheme that thinks about lunar construction and the creation of infrastructure from a comprehensive, holistic perspective that can feed into a master plan, or what I would consider, or what I would call a kind of anticipatory approach to lunar-based planning, which leverages and accounts for the needs of multiple stakeholders, both on the commercial side as well as the government side and the defense side. So this is a study that I led prior to joining ICON. This is a lunar landing pad study where we were beginning to consider what exactly the needs and requirements from a civil engineering perspective a lunar landing pad might be and might require. Additionally, we looked at what a foundational surface habitat might be for a crew of 4 over the course of a 6-month-long mission in this case. And these types of studies have enabled us to think about, like, over the course of time, how these various infrastructure elements might relate as far as their adjacency is concerned, their location on the south pole of the moon, which is where we've been focusing much of our attention on, and how exactly we can create permanent infrastructure that is useful, again, for multiple stakeholders. I think this is an outdated slide to the one that Mark previously showed, but we're starting to think about and starting to collaborate with various NASA centers, in particular Kennedy and of course Marshall, to think about how we can leverage excavation capabilities supporting construction on the moon. Certainly we can't do this all alone. We're not developing our own power infrastructure, and we're going to need to collaborate with others on that. But in our case, we're very interested and invested in ensuring that we're designing structures that can meet the needs for, again, multiple stakeholders in different sectors. So what we're developing as part of our SBIR are directed energy deposition technologies, utilizing 100% ISRU regolith without the need for additives and binders. And we are developing these and planning to basically engineer a robotic manipulator that will be aboard a CLIPS lander, anticipated to conduct an initial construction technology demonstration mission sometime in the 27-28 timeframe. So this is our goal in the near term. That robotic manipulator will scoop, sieve, and then sinter local and indigenous regolith, and then validate the structural properties of that initial sample on the moon. Of course, I mentioned we're supporting the Moon to Mars Planetary Autonomous Construction Technologies project. Our terrestrial construction operations, which leverage cementitious additive manufacturing, are teaching us a lot in the short term about what it means and what it takes to actually autonomously construct habitats and other structural elements such as this. It is no small feat. Everything is a challenge in construction. And I'll end really quickly with a construction demonstration that we completed at the Johnson Space Center a little over 2 years ago. This is the construction of the Mars Dune, well, I shouldn't say Mars Dune, the Crew Health and Performance Exploration Analog, the CHAPEA analog, which we affectionately refer to as Mars Dune Alpha, since nobody can remember what CHAPEA stands for. And essentially, we 3D printed this designed this 1,700 square foot structure within Building 220 at the Johnson Space Center. This is directly opposite and adjacent to the Hera analog, and I'm very excited to report that ingress for the habitat and for the experiment will begin in June, so very soon. There will be four volunteer crew members who will be living in this analog for 1 entire year, which is the longest analog mission that NASA will be completing to date. And we're very excited to see what the results of that mission yield and how it establishes standards and guidelines for future long-duration missions. Thanks.
Great, Melodie. Thank you very much. That's you know, even now, we're looking at 3D printing on that scale. It looks like we're watching a 3D animation. It's hard to believe that actually can occur. Next up, we have Sam Ximenes. Sam is a space architect with XArc. Am I saying your group name? Space Exploration Architecture Corporation. And with that, Sam, take it away.
Sure thing. So I'm going to talk about a subsidiary of XArc called Astroport Space Technologies. And by the way, thank you for giving me the opportunity to talk about this work that we're doing for lunar construction and as well as Mars. We're using the processes that we develop for the lunar construction and the infrastructure we want to develop as improvement ground, of course, for what we do on Mars. We're focused on landing pad construction and, again, the horizontal structures, but we're working with a different material form factor, and it is the regolith, and it's the pure regolith, just like Icon is working with, without the binders and the additives. But we're working with bricks, and we want to learn, the bricks are basic building material here on Earth, and bricks are used in all kinds of applications, from roads to foundations to structures. So we're working with the development of the bricks and how do you melt those bricks, and how do what is the use of the material, what it can do, what it can't do. Let me show a video here of the overall concept of how we approach
Moon
the landing pad
travel
construction.
is back, and with it, opportunities for habitation on our nearest celestial body. Exploration Architecture Corporation, known as XArc, and our subsidiary, Astroport Space Technologies, are developing ways to enable people to settle on the moon and beyond. These new advancements could play an important role in bringing space exploration to the next level. Along with our research partners at the University of Texas at San Antonio, known as UTSA, Astroport has designed equipment that will convert raw material found on the moon into durable material that will be used to build lunar infrastructure. Here's how it will work. On the moon, there's a layer of loose, rocky material covering the bedrock. The bulk of the surface is a fine gray soil known as regolith, which is considered toxic to humans and machinery. It's abrasive and electrostatic, so it clings to spacesuits and gets in gears. And if it gets inside the habitation area, it is a health risk. But that soil also has a good side to it. Astroport has developed high-tech machinery that will ultimately use this regolith as building material to provide solid surfaces for roads or moon landings and takeoffs, accommodating a variety of spacecraft. The first step, create a process for turning the moon's surface material into brick. Researchers and scientists at UTSA are determining the exact temperatures needed to liquefy different combinations of moon soil to turn that melted material into extremely durable bricks. They're also conducting experiments on how much energy is required to melt the soil. Astroport and UTSA researchers have designed a tool called the Lunatron. It's an integrated induction furnace nozzle for forming and placing lunar regolith bricks for the landing pad construction. This machine gets feedstock from the surface, sifts it through a screen, heats it using an induction heating coil to melt the feedstock, then forms it into bricks and places it where it needs to go, all in one step. This technology is particularly groundbreaking, as there is no binding substance required to create the bricks or keep the tiles together once they're placed. Robots, known as brickbots, are deployed to assemble and place the bricks produced from the furnace nozzle into a reusable landing pad. To prepare the surface for the landing pad, an excavator and grader robot smooths over the landing site where the bricks are laid. Then a hauler robot takes the excavated regolith to the brickbot to be filtered and used as feedstock for making bricks. Once the landing pad is constructed, another regolith machine known as a RegoPack, short for Regolith Particle Acquisition and Containment, bags the regolith. It does this in a continuous manner to make long sandbags that are used to build the blast shield needed in case of explosions. When complete, the landing pad will provide a safe landing port that can be used to facilitate reliable and efficient space flights to the moon, Mars, and beyond.
So we're putting our money where our mouth is, and we're actually making the bricks. This is where we're at right now. We've been able to make the bricks in vacuum. The ones you see here are ambient bricks that were made in ambient air. But we've just had a breakthrough with the ability to actually do this in the vacuum chambers. And that's very important because we have to be able to prove that we can work in the same environment as on the moon. The other part is on the next slide is the test of the process, and this you see here the same drums that you see on the razor, but it's not really doing the excavation. It's doing at the top level 10 centimeter grab in the regolith for the feedstock that we'll use for the test bricks. So this is our technology test demonstrator that we'll use with our robot. That is, next step is to actually integrate the two. On the next slide here, is that for me? Yeah. So what we want to do is we want to integrate that nozzle with the razor drum, and then provide the demonstration and proof of concept that these bricks can actually be made on the lunar surface, hopefully by 2027 timeframe. And then we think, we're looking at 2030 is operational with the Lunatron. Now that's the brick making part of it and the actual materials that we deal with. The other part is going to be the site preparation piece of it. We've been looking at an actual ConOps as to what does it actually take to prepare the site and do the excavation of it, and actually by choosing a particular location and actually looking at what's there, what are the contours of the terrain at this location. And what comes out of it is that it's very critical that you really have to choose where you're going pretty much before you get there, because even distances of a few hundred meters will change your excavation profile in terms of what you have to cut and fill and what you have to dig. So you can see here some, just in these three different options here, there's some leveling of excavation that really has an impact on how much you have to dig up. And I don't think people have a really sense of what the capacity of the bulk regolith we have to dig with. I mean, we're talking about, as Mark mentioned, tons of regolith and we're looking at 20,000, probably even 50,000 in some cases of regolith that has to be moved around. You see a small little dot there at the top of the screen? That's a 95th percentile human male. So you get the sense of scale, okay, in terms of what we're talking about, in terms of the bulk regolith movement. And in the middle screen there is just the movement within a 330 meters square area of where you put. You can't really see the square part, but those three circles moved around within this 330 meter area, and you can see the differences in what the amount of regolith has to be dealt with in terms of the cut and fill as well. So it's going to be very critical that we send out there first a surveyor robot, essentially, civil engineer and surveyor robot that's going to really measure out the site and understand what's there, so we know what's the geotechnical properties of that location. And then you got to start dealing with the design and the engineering of the pad itself. Do you level? Do you actually do a cut and a fill method where you're actually doing leveling on the surface? Or do you do it, or do you dig down to get down to your level part of it? Is there a benefit between the two? These are trades that need to be developed in much more detail. And the case that we came up with for the leveling, you see the volume in this particular site was 30,000 cubic meters of dirt. You need it for, part of it is going to be with the actual site prep, relevant piece of it. You'll need some soil for the actual feedstock we need to have for making the bricks. You'll need the soil for the building of the berm. And then in our case, where we're doing these regol packs, we'll need some soil to fill the covering of the berms with the regol packs as well. If you go down, if you dig, you see the difference here. We got almost 50,000 cubic meters of dirt that needs to be dealt with. The same amount of different variations. But now what happens here, on the first one, if we level on the top, then we don't have any feedstock for the making of the bricks. Now we have to go somewhere else and dig out and excavate another location to feed our brick maker. So it turns out that the leveling by digging down is even better for us, even though it's got a higher volume of regolith. But again, as I mentioned, it's all site dependent. We were able to eventually optimize that site and locate just a few meters away, another location that's flatter, and we're around 26,000 cubic meters in this particular site we're looking at this point in time. It's a little light there in the profiles of what we have to cut. You can see here when we start going down into the geotechnical engineering pieces of it, you need to deal with things of shear strength, bearing capacity for the landing of the rocket on the pavement. The light blue here in the bottom part, that's the amount that was cut out to dig that leveled out area as well. So again, now we're into the engineering piece of the actual pad in this particular design. After that then, or not after that, but in parallel, but now what's the site layout? What's the activity that you have to deal with when you get down there. When you land initially, you have to bring all your assets with you, your digging tools, your implements, your tractors. And that's going to be a different location than where you're going to actually make the pad. So now you have to cut roads. You have to cut a path to where you're going to actually make the pad. And then but first, before you do that, you need a road to where you're going to set up your power system, whether it's the solar panels or whether it's a nuclear power source. You need to set that up as well. And then you need to do the excavation part of it. You need a borrow pit where you're moving and dumping dirt and piling up dirt for different aspects of the road building and the pad building, and the charging station and equipment storage. All these assets have to be dealt with in terms of the con-ops that needs to be put together. You see on the right side there that the green long winding road. That's to where the habitation area is going to be. So you're making this site layout away from where your habitation area is going to be, and we have it at a higher elevation as well, because we want to be able to be lower when we actually are taking off, so that you don't have residual dust and plume raining down on your habitation area. And then we go into the con-ops development itself. And so all these tools and all these assets that are brought to the surface, what's the flow rate? What's the timelines you need to deal with? And what's the concept of operations for the first things you do when you do your staging, you land, you stage. How does that get put together? How do and what are those timelines? And what that does, though, is that generates the requirements for the power requirements. So we're not there yet. We're still in our study about this, but we're turning the corner on this and trying to understand these. We're doing a lot of simulations, and this helps us with the traverse timelines, and that then translates into the power requirements. Part of that also is we're starting to work into a digital twin to make those simulations work out as well. So in summary, I think I want to leave you with the message that this is not a trivial task. I mean, we're going to be taking a formal undertaking to move all this dirt around, and there's going to be swarms of robots, and especially when we talk about lightweight robots with bucket drums that have a limited capacity of volume as well. And just recall, this is a lot of dirt. Thank you.
Great, Sam. Thank you. But let's put our hands together for everybody's opening statements, please. Quick housekeeping question here for my tech brothers and sisters up there. Our clock here, is this for until questions, or is this our full time? Okay, very good. Okay, so I'm going to immediately go off script here because Sam said something there that I thought was really a better place to start. And he used the words, quote, unquote, the site. So let's talk about the site. In the Mars world, we've spent decades arguing about the best spots to land rovers and eventually humans, and have actually had some luck in conferences like this to influence those decisions for the better. Maybe a little more dangerous, but more interesting. For people who think about the moon, we Mars people don't think about the moon that much, but people who think about the moon, you must go back and forth on what is the best site at the South Pole. Where do you get all the factors you need to do this? That is a lot of dirt. Where's the place with the most good dirt without the least boulders? And for our discussion, let's talk like we do at my house. I don't think my wife is watching this, but in other words, let's interrupt each other. Let's talk and let's open up the flow here and talk. Where Mark, Seamus, Melodie, where is the site?
I think it's where you can best achieve the goal you set out. So, for example, if you're trying to build like an X-ray telescope, it should be on the far side. If you're trying to be near PSR, partially shaded regions where you think there's water ice, South Pole. If it's for ease of access, and looking at things like skylights on the moon, it could be mid-equatorial. So I think it depends on the goal that you're trying to achieve. It's just like everything else. If do you want to move to Texas or do you want to move to Montana? Yeah.
Yes, but Texas and Montana have a lot more in common than the equator on the moon and the South Pole. Yep. So let's talk about it from the perspective of a semi-autonomous, semi-permanent human zone. Where is the site?
think we're looking for something that has the resources that we need to eventually build upon and survive on, right? And I know NASA's done many studies to try and identify, we picked the South Pole. So then there's a multitude of locations, there looked at to, satisfy science goals. But I mean, ultimately, if we're talking about in this forum, how to develop a sustainable somewhere, we're looking for where are the resources. So the water ice, potentially. You might want to be on high ground so that, one of the benefits of the tall tower there was to get those solar arrays out of the shadows, right? So you can have your continuous solar power. So specifically finding locations that are going to, like you were getting to, meet your particular goals is really critical. So for sustainability, you're looking for the resources, I think.
But there's some consensus at this moment of the South Pole for humans. Is that a fair statement?
I think that's driven by the particular looking for the presence of water.
Water ice.
Looking at water ice, and to be able to then generate material and useful things from that, particularly rocket fuel, that could provide an infrastructure to then expand around the moon. I don't think that the South Pole is, we get there, we settle, we're done. We don't go anywhere else. I think the reason the South Pole is of interest is it may provide the best breakout point for going around to different areas of the moon. If you land in the equatorial region, you're in the equatorial region. But if you land, if you build around the South Pole and you're able to process and develop rocket fuel, now you're talking about being able to hop to places. Now you can have a transportation. I mean, it sounds fantastic, but you could have a transportation system that you're not waiting on tankers coming from Earth.
We're into space 1999 here.
Exactly. Yeah.
Very good. Great show. Undersung. Melodie, any thoughts on this?
Yeah, I think there's a huge emphasis on developing a commercial lunar ecosystem for exactly these purposes: industrialization, commercialization, and thinking about how we can leverage water ice in particular to create rocket propellant, and many other byproducts, right?
We talked about talking about getting the initial gear and equipment from Earth. So let's do that, but let's also talk about, in the context of that, power and all of your kind of dream power systems for what would make this work best. Sam, your presentation was super cool, but man, that's a lot of dirt getting moved around. I don't know how much you can do with solar, or how much. What are our power options? Let's start there. Let's talk about power for a couple minutes. Anyone?
Yeah, I think that definitely going to have to work with nuclear power. In NASA's, of course, and other agencies are working with the kilopower reactors right now, and we're on that path. But I don't know if they'll be there in the time frame that we will be there initially for the first outpost. So it's probably going to be solar power in the beginning. So there'll be some, it's going to be a phased approach, of course, in terms of the complexity of the infrastructure that you built there in the beginning as well. If I could just go back to the site question real quick.
Yeah.
I think that it's not the site, it's where's the first site.
Yes.
Because there's going to be multiple sites. And it's rapidly becoming a geopolitical question because there's going to be the resources that we need to have, where are the resources that we're going to go to as well. And in my opinion, the resource is not the water, the main resource, it's the light, the sunlight for the power. And that's where I think is where it's going to be driving, as well as the water part. I'm sorry, go back to the power part.
Very good. Very good.
I was going to say, that's why a lot of the sites you'll see are clustered around the Shackleton crater rim.
Light.
I think from a power, sorry.
So initially, we already, systems on the moon, that have landed there, have used anything from power cells, which is what Apollo used, to now solar. If you have a nuclear type, it seems attractive, but then there's the infrastructure you need to distribute the power. Whereas solar seems to be more of a localized grid effect. It's similar to on Earth. I have solar panels on my house, on my own generation system. I don't think I want a nuclear power plant in my backyard. So the challenge with these very high power systems is you still have a distribution problem where you got to run cables, you got to run things around, you got to beam the power with its losses, and so solar seems to be the thing that's, even though it's linear, if you need more kilowatts, you build another thing. If you need, it doesn't, you can't exponentially ramp up your power. It's linear with mass. That seems like most likely candidate, particularly with the areas where they've identified that are permanent mounds of light. They have some phrase for them, I forget what it is. Where it's uninterrupted sunlight. What is it?
Oh, she said peaks of eternal light.
That's it. Thank you. Peaks of eternal light.
Peaks of eternal light, and those would be on the poles.
Yes.
Melodie, can you talk a bit about initial infrastructure and getting stuff to the moon? We live during this time right now where everything's changing really quickly in terms of our potential to move gear and equipment off Earth, and it actually, as you talk about solar, for example, the solar's funny that nothing's exponential, but it just keeps getting a little better, and then you get it to the moon, and all of a sudden it's better still, right? Because that's, again, like your tower without wind. Solar works. If you can get 24/7 with solar on the moon, you'll get even more output. Talk about your goals for getting stuff there.
I mean, I think Sam showed us best, right? Like it isn't economically feasible to anticipate that we're going to launch tons and tons and tons of construction materials to space. And I think that's the point about ISRU construction in particular, is that we want to send a single system or a few highly reliable systems that can work over the long term to create the various applications that we need. I don't think, even with the great strides that we've made in transportation in recent years, and that's happening on the commercial side, I don't think we can anticipate a moment where we're launching like hundreds of thousands of tons of concrete or cementitious-like materials. It just seems prohibitively expensive, and I don't think it's going to be a sustainable strategy for long-term growth on the moon or Mars.
But while it's, I agree, but the tyranny of the gravity well of Earth, while at the same time, in the last decade, the number of opportunities and the different alternatives you have of getting tools and getting equipment to the moon has greatly expanded. So there's this nice, the thing that's accelerating now is all these different companies are developing a capability to commercially deliver, relatively smaller payloads. So yes, you're not going to drop, rebar and concrete, but getting specialized tools, getting equipment to the surface will not be an impediment to the kind of designs that y'all are coming up with.
Yeah, I think the trick is thinking about large-scale infrastructure, right? Like that's where the scale problem really becomes apparent. If we're talking about landing pads, if we're talking about roadways, when do they become necessary? When is it just reckless not having those? And for how long can we sort of maintain or sustain a human presence without that kind of infrastructure?
I want to talk a little bit about modularity of tools and the idea of being able to reuse different stuff for different stuff projects. But before we do, I want to ask a quick question about the dust. So when I see Sam's presentation, I see it doesn't look at all like my side yard. It looks clean and tidy. Everything is pretty neat. It's not. It looks to me like the goal here is to get the dusty regolith out of the human living space. Can you talk about that?
Yeah, that's I think the most critical thing that we have to overcome is the dust mitigation part of it. Both in for the video said, for the internal living inside the habitats, but also for the machinery outside. And there's all kinds of concepts out there for dust mitigation for the external activities. from mats to, to bricks to, to other, sprays or whatever. So that's being addressed, but I think it's really not solved yet, especially in terms of the machinery. The machinery, so the regolith is very abrasive. It's going to tear up all these implements real quick. Okay, it doesn't. I mean, you can see what when we have to have talk about the inventory. We'll need to bring spares and additional implements to replace the stuff that's being broken down and torn apart. That happens here on Earth. It just is the way you do things, do construction here. So the dust is going to be a real problem, and where it's being worked, but not solved yet.
Are there any just outlandish ideas of how to deal with dust and that did we talk about like setting off a small nuke above the air, blasting it all away? You start sort of something fresh.
So one of the problems with the dust.
Seamus likes this idea.
One of the problems is on the excavation side and the conveyance is the fact that the dust it's electrostatic. It sticks to the sides. Even the material you use for your hoppers will be a problem. You have to deal with that. So you have to and there are some technologies that we're looking at that can solve some of that electrostatic issues that we have to be overcome as well.
I think Neil Young saying that rust never sleeps. On the moon, it's dust never sleeps.
Yes.
More thoughts about dust before we talk about modularity.
Yeah, I think it's going to be a multifaceted dust mitigation plan. I think establishing dust-free zones around your site just to mitigate the trafficking of dust in and out of your habitats, having dust-resistant seals, connectors. Some of those dust mitigation techniques could be passive, some of them could be active, like electromagnetic dust shields, which NASA's helped develop, for example. How do you keep dust off of your optics if you're using those for surveillance or machine vision, that sort of thing? But a whole suite of technologies being considered, I think, all play a part.
I mentioned modularity before, and I'm going back to my own toolkit. So I'm a Makita guy. Okay, so that's at some point you marry power tools, and that's what you use. Now, was that a good choice or not? I don't know, but that is the infrastructure that I work with because those are all the batteries that I have. Okay, so let's talk about modularity for a little bit. How do you now would be the time to start thinking about a baseline concept of sizes and parts, what's needed, and how you can share this stuff. Your rover broke down, but we'll sell you some wheels from ours, but because we know they'll fit on each other. Let's talk about that.
Yeah, we're definitely working a lot along those lines, thinking about modularity for several reasons. One is you saw the image on one of my charts earlier of a common platform that can then be customized to do different jobs with different implements, right? And so modularity to enable reconfigurability, but then also modularity for repairs. Well, these systems are going to break down, and so we have to expect that. We want to design that into our systems. The excavator that you saw there is not modular in the sense that, I mean, you can take it apart obviously, but it's not modular in the sense that it's amenable to quick replacement of a bucket drum, for example, something that would be a wear item. So we're taking modularity very seriously. And on top of that, standards of the connectors so that, multiple entities can know how to build to service somebody else's, common standards and that sort of thing.
So modularity is not necessarily the goal, I think, is an approach. The goal is to minimize the mass you need to transport from the Earth. And if that is by making things modular, that would be great. But it may, another approach may be, to have tools that can make tools, that have, what do you do with waste product, that is spent on the surface of the moon? We might have landers that when they land, they never leave, and they become, wreckage, but that is mass that has already been delivered to the moon. How best to utilize that? So I think the goal, and modularity may be an approach to reach that goal, but the goal is to minimize the amount of mass you need to bring from the Earth, because that is really the cost driver. That's in all these things.
I agree. Particularly for private companies, mass optimization is key, and it's what we need to consider for profitability, like bottom line. I'm conflicted though, because I do see the need for standard interfaces and modularity to be incorporated in the way that we're engineering these systems, and incentivizing that in the private sector is really, really challenging because it is a competitive landscape, right? So how that happens, it remains to be seen, but I do see that there being a clear need for standards and guidelines relative to shared interfaces.
And at this point, are you in the industry talking about that? Are you having panels like that at your conferences and starting to get the ball rolling there? Yeah,
We have.
Yeah. You know, there's another panel happening right now that I would be in if I weren't here, and I'm glad you're all here. And that's more the kind of the labor on the moon and Mars and in space, and the kind of skill worker. Actually, I'm gonna take 2 seconds again because I like to toot their horns. I want to take 2 seconds to applaud our tech staff here. So that would be Wade and Valerie and everybody up there. Give me a good little kiss. I mentioned last night at the screening that in my mind, a perfect Mars, but we can call it Moon crew, is some high-level functioning scientists supported by tech people exactly like Wade and his crew here, because they're problem solvers. You need people who can solve, and we know people like this. We all have friends like this. I fancy myself a good mechanic, but not nearly the mechanic some of my friends are. Mechanic's not even the right word. They just find ways to fix anything, anywhere. So I would hope that next year we could maybe try to integrate a panel like that where we talk a little more of. But anyway, that we're putting the cart before the horse here. Sam, did you have? Oh, we have a lot of questions. Lord have mercy. Okay, we're gonna turn this over to the audience, and I can't see anything out there, so we'll start with one on this side.
Yes. I think Sam mentioned some bots built to make landing pads. Is this only for landing pads, or could it also be used for other buildings?
The bricks themselves, not just for landing pads, it's roads as well, roads and any kind of foundations. Any sort of structures that need to be retaining walls. So it's all kinds of ways that we can. So one of the things is that you saw Melodie's approach to the landing pad. You saw our approach. There's not going to be one solution for this. It's just like here on Earth, the construction technologies are multiple and varied, and for different applications. It's going to be the same thing up there as well, as we get more and more infrastructure developed as well.
Okay, thank you.
Right, very good. Let's go to one on this side. Switch back and forth.
Sam and then Seamus, you slightly touched on the issue of spares. I think I'm a little too close to the mic. You touched on the issue of spares. Obviously, you're talking mainly about building the bricks and then the sandbags full of regolith. We know that Blue Origin recently, earlier this year, came public with the plan to make solar panels out of lunar regolith. How far down the line do we start thinking about making the building machinery itself on the moon, or components of it, spare parts for the diggers and everything like that?
Yeah, so our long-term business case is to become the operator of these landing pads, not just to construct them, but to be the fixed-base operator, like they do at aircraft or airports here on Earth, where you have a company that's actually doing the maintenance and the fueling of these coming and going spacecraft. And part of that becomes a depot. So in that depot, it's a maintenance depot. It's called MRO, Maintenance, Repair, and Operations. And in that depot, we'll have these 3D machinery to take recycled materials, the landers themselves when they land. Some of these concepts have a descent stage that doesn't go away. We have to take it off the pad, and well, that can be recycled, all those metals. And we have technologies that we're developing to actually recycle those metals and turn those into material for other things as well.
Yeah, just adding that, I mean, anytime mass gets to the surface of the moon, it becomes very valuable. And so in addition to the maintenance depots, I think it used to be very sophisticated junkyards.
Exactly.
Where You know, it used to be cars were simple enough, I'm not sure it's true anymore, that if you needed a part, you went to a junkyard, and if you found it in a junked car, you took it off and put it in your car, and it was, good job. That will have to be something looked at, because getting, a kilogram to the moon is still going to be very expensive. But if you can make use of what's already there and is waste product, essentially, then all the better.
That touches on what you were talking about earlier, and I don't disagree with what you were talking about with the recycling or repurposing of stuff. I think it's really important to, like cars nowadays are designed to some extent with recycling in mind, right? Mm-hmm. We need to start thinking about how do we design our vehicles that once they've served their purpose, they can be, and we have a whole other initiative that's doing recycling and repurposing of materials because we understand their value. And we're also working on the problem of designing for not only modularity, but being able to accept 3D printed parts and 3D printed parts from in situ resources. And we start talking about, do we have to hold the same tolerances that we would on a terrestrial vehicle? Those sorts of things start to flood your mind. Can I build that part good enough and have it still serve as a functional spare? So that's a really good question. It's something that we're definitely thinking about.
Great, yeah, great, thank you. Next one over here.
Is this working? Okay. Okay, I was wondering, how will the robots, like when they're working on turning the regolith into proper building materials, how will they be monitored? And is there like a plan in place to deal with what happens when a robot breaks down?
Oh, this is a great question.
Question.
If you couldn't hear it, how will the robots working autonomously or together, how will they be monitored, and what will happen when they break down? And I'm going to jump on that question with a tangential question after we get through these questions, because I have one similar.
Can I jump on that real quick? Because that's one of the areas that I'm really, into amongst all the others. But having in situ monitoring of the processes as they're happening. So, like I know Melodie and Sam, you all are probably on board with this. Is as you're building something, you're looking at it, maybe the thermal profile of your melt or your weld bead and that sort of thing. So you're monitoring the process, and you're giving that feedback to the system. So if it has to take corrective action, it can. And it's all being done autonomously, so you're developing the autonomous logic that the machine can make those adjustments itself. And as far as the breakdown, that's also a great point that I didn't make earlier, but that is having systems that can understand their own health so that it can anticipate a breakdown and schedule its own maintenance, right? You don't want to have to go 100 kilometers away with a lunar tow truck and pull your excavator out of you want to have some sense of when it needs to be. And with that, I don't know if anybody mentioned it, but digital twinning, right? And so having computer models that can take on sensors data from the actual machine and correlate it to a predictive model and say, that bearing, it looks like it's about to fail based on sensor A and sensor C torque readings or something like that, right? So really important areas to be considering. Yeah.
Thank you.
Okay, over here. Here's a couple suggestions. Sam, sell people the ability to have their name put on your bricks. I might pay $50 to have my name put on a brick, and probably would buy some for each of my grandkids. The other suggestion is
we are doing that.
The other suggestion is when you're
Sam's idea.
That's right.
When you're screening out the rocks, don't throw the rocks away. Use them to fill gabion cages.
Oh, that's a good point.
Yeah.
So we see the regolith that we dig up that's not used in the construction. There's going to be a lot of leftovers, all the slag essentially, and what's left out of the filtering. That's a commodity to us. That becomes like essentially a material yard where we have piles of different types of grain sizes and particle sizes, and those become commodities that we can sell to other companies to try to do like the mineral extractions and the metal extraction. So that's really a part of our business case, is to be in the business of selling material.
No,
that
I
we've-
think
that we've dug up
Ambion
already.
cages could be used to build blast walls and radiation shielding walls, and
All
you
that.
could even make a trapezoidal one and make an arch structure. So.
Very good, very good. Next question over here, please.
Yeah, in the conversation around staging materials and the logistics and building this out over multi-years, and in relation to what you were just talking about with the autonomous vehicles, where does communication links fit into this? Because I'm thinking even though the vehicles are going to be autonomous, if someone yells for help, there's got to be a way for that yell to get somewhere. And building up the communication links, I would think, would be a vital integrative part of building out the whole logistical infrastructure.
So we just recently announced our office opening in Luxembourg. And we're doing that there because we want to tap into the ESA Moonlight program, which is their satellite communications network. And we'll be using that for a lot of the position and navigation. Now, there's other, Lockheed Martin just announced that their own system as well. There'll be a number of communication networks being developed for satellite operation and control for surface systems. So those are those options that are available to us, but we'll be working with the European Space Agency in our concept.
So as you're developing your plan over the multi-years, is part of that plan looking at how the communication?
Absolutely,
Yeah.
yes.
Thank you.
Hello, my name is Aon McNeil, and I was wondering, with the CHIPIA analog going on, how is the furniture being created? Because I see a lot of hard surfaces with 3D printing, and any of the comfort softer materials would have to be brought from Earth. So I was wondering if there was any research into maybe growing a material like mycelia to bring in the comfort element that can maybe be scaled up.
It's an excellent question. There's absolutely research happening at NASA, also in my own team, as to how we can outfit structures utilizing local materials, both polymers, but also in situ regolith over the long term. That's very applicable, and I think there's lots of room to develop those concepts further. In the case of the CHIPIA analog, we had nothing to do with outfitting, unfortunately, or whatever, but basically it was left up to NASA, and for whatever reason, they felt like Lazy Boys and IKEA furniture would do it. So.
Well, who doesn't like lazy boys? I mean, and plus the mass issue there, they're lightweight.
Yeah. I mean, it's only every once. It's only once in a while you build a multi-million-dollar research facility. But in any event.
Chris, I see you lurking over there. They just bought us a couple more minutes here. Look, yeah. Okay, very good. Hold on, Lord have mercy. He's got the gas tank, Okay. No problem, buddy. Okay, very good. We, Beth.
One more.
Yeah.
I'm glad we're talking about analogs. So I would be amiss if I didn't ask about Hawaii's High Seas Research Center, where we have some perfect conditions for some very porous rock that is similar to Mars. And I want to ask the panel, how about, or any thought of, starting to build under the lava tubes, under the surface, mitigating the dust on Mars?
So I'll take that. So we have another project called LEAP 2. If you go to our XArc website, YouTube website, you'll see videos about our concept for turning the Marias Hills skylight, the Marias Hills hole, into a settlement area for lunar settlement. We're using the lava tube that's there as a way to make a full-blown scaled community as well. So yes, we're looking at that.
Thank you.
A little tangent to that. One of the things we're going to need to have is lunar proving grounds here on Earth. All this construction material, we need to really start talking about our network of the lunar proving grounds that we're going to need to be able to use to test these machineries out as well. And those are going to be scaled from controlled environments to outdoor full-scale machinery that can be tested and proved before we can get up there.
And analog astronauts break things really well and test them.
We fix them well,
fix
too.
them well too. Yes, thank you.
Thank you. When I saw this panel laid out on the page, there are going to be lines of questions because it's just such a ripe topic. You want to see some questions? Here's a page of questions I didn't get to ask because. So I look forward to the next time we do it. I'm going to get to your question. I look forward to the next time we do this because there's a lot of ground here to cover. Many more specific questions, and I'm going to try and sneak my question in still too. So next, sir.
Hi, my name is Ari, and my question is slightly maybe different from what you've been speaking most of the panel. Here on Earth, construction also involves permits, regulations, but you haven't touched on this topic. So I wonder if you could share something about what is really happening in terms of how tall can you build something, or where can you get the permit to do something, or what are countries really talking about in terms of who has a right to do what and where? Thank you.
Yeah, that's definitely an issue. The one thing that I'm currently involved with is the American Society of Civil Engineers, and they're starting to pull together sort of a framework for building standards, just to start. The whole idea then of permits and all that and regulations is a little bit above me. I'm not so in touch with that. I imagine it's going to have to go along the lines of what we were talking about earlier today, of the sensible use, right, and not, digging in areas or populating areas that they don't want us to be in. But in terms of developing standards, that's definitely an important thing that we're currently working with folks on. So.
I can jump
and on the other side of it, it must for architects, it's also a dream slate, right? A place without building codes and where you can.
Well, yeah. I mean, you can look at it that way. The other way of looking at it is, well, when you're building terrestrially, you have to permit structures according to authorities who have jurisdiction, right? On the moon, we don't have a framework for that yet from a regulatory perspective. So I think that standards and guidelines are sorely needed. Just to give you a sense of how early all of this is, like there isn't even international building code for additive manufacturing terrestrially. So we're appealing to appendices that are written by like the International Code Council. It's not standardized by any means. It's not universal, and we have a long way to go. But it's exciting for that reason. Like it's one of the reasons why I like working in this industry so much.
Okay, great. I think and great questions from everyone. Great panel. Thank you guys so much for doing this today. And it's a strange. No, Chris. Okay, no, it just went back to zero. No, it was going backwards for a while. You saw that. Yeah. Okay. Yeah. All right. Oh, is that what that was? Lord have mercy. Okay.
You kicked me off before.
Yeah. Okay. Yeah. All right. Very good. So. All right, very good. Chris Carberry, ladies and gentlemen, is going to kick us off the stage here. Thank you all for coming. Chris, anything you need to announce here?
Well, we have one additional speaker. Another final speaker of the day, so I'm going to announce that. But before I do, also, for those of you who haven't signed up, anybody interested still who want to go to the Rosewood Hotel reception, there are still some tickets left. I believe the QR code is still at the front door, and I think you can still buy them for $60 at the door as well. Beautiful rooftop venue, so hope we'll see you there. Otherwise, I'm going to introduce our next speakers. So.
Thank you all.
Thank you. That was great. I look forward to watching the whole thing.